Alright, engineering students, welcome back to the very first video of the second semester. I'm excited to start up again, and we got so much planned. We are going to do about 5 more weeks of statics still. Okay, we're going to do 2 very particular applications using everything that we have been doing up to this point. And those 2 applications are in the textbook. The first one is trusses, and the second one is beams. I'm going to talk about that a little bit later, but just wanted to give you an idea. After that 5 weeks of more statics applications, we are going to switch tack completely. Switch tack, by the way, is a nautical term. It refers to when the sailing boat flips the sail from one side to the other. And we're going to go into robotics and coding, and we'll stay there for the rest of the year. Before we get into anything else today, though, I want to update you guys on the community design projects that we've been working on. So this is a collection of screenshots. I took the Gil Addison design that team did, and I just spent a few hours. I actually copied it to a totally new document, so you won't see these changes. I have like my own kind of admin level one now. And I spent a couple of hours just cleaning it up, making things work a little better, thinking of some changes to the designs. It's overall more or less the same, but there were a few things that I saw that need to be fixed or different ideas. And this has gone to Gil. Okay, I zoomed with him and showed him all this, and he's pretty stoked about what is on the screen right now. Let me just talk you through it quickly. We have in the upright position, okay, which is these 2 photos right here, you can see the actuator is fully retracted, okay, and I have to be very careful trying to get the right one on Amazon that has exactly the right travel and length and dimensions that we need. And this little keyboard thing here, this is the idea that I had. It's pretty simple, I hope, but essentially there's this little nut right here. It's like a big plastic nut that screws on. I actually didn't model it, but there's a screw that runs down through here and then has a head underneath the plywood surface. And so as you turn that big screw, that is going to let this thing pivot up and down just purely based on its own weight and the person's hands resting on it. So this is almost in the fully upright position here. Actually, it's fully up in this image right here, and then it is fully down in this image here. Again, that little screw would run through with a head underneath the plywood. And yeah, you just turn that knob, and that will, in a very manual kind of way, adjust that keyboard to a different position. We've got full adjustability as well, don't forget, on the actual screen of the iMac, so that'll help the user. And I went with a slightly different design. Notice that in the fully upright position, I'm trying something where the upper surface is actually not horizontal relative to the table. You see that? It's got a slight angle. I actually have I think it was a 10-inch center to center strut here, and then a 10.5-inch center to center holes strut here. And the reason for that was because when it dips down, like you can see in any of the other 2 images, it kind of exaggerates a little more. Okay, the angle gets a little steeper, but it's actually going to help it as the actuator has to pull it back up into position. It'll actually help it mechanically. It gives it a moment advantage, actually. It gives it a stronger moment when it comes time to like lift that and raise that back up. If those 2 struts had been the same length, which is how they had been up to this point, then the upper surface would be horizontal, if you can imagine that, and then as the thing pulls on it, it's a little bit hard to describe, but basically this distance here, that green I just marked, that is the moment distance that this thing has to pull and generate a moment to raise it back up. And if you didn't have that extra advantage, you get a much shorter moment arm. I'm getting a little technical there, but hopefully you can maybe get the gist of what I'm talking about, if you can imagine it both ways. And it also just helps it like dip down, okay? Having that 10.5-inch strut makes it dip down more to be pointing down at a wheelchair user. Okay, so all these things are very, very aimed at the client. And I did check with Gil, and he was absolutely adamant that he wants both the upright position as well as the fully lowered position. He would use it as an upright standing desk for ambulatory persons, and then right down for wheelchair bound persons. Everything else is still there. The clamp, the actuator, I added a keyboard to Josh's computer model. I put in the power strip that Hunter made, so it's all there, and I'm pretty happy with it. And I think it's very reasonable. It's actually probably a very simple build. It's really just a few pieces of plywood, a few maybe like oak struts or something, just for a really hard, firm wood, and getting that actuator just right. So that's on me to start to put that together this coming month. Or this month. It's January now, isn't it? Here we are. All right, I think that's it. I'll show you guys Mrs. Jones' model in the next video, the second video this week. And maybe I'll have another little surprise object to show you as well. But here we go. Let's get into the first of our two statics applications. The first one is trusses, and I said the second one coming up in a couple of weeks is beams. Now, these photos here, these are all examples of trusses. Some of you may be familiar with this term, others not. But a truss is when you try to create usually a large, rigid, here, let me list some descriptors here. Usually like a large, rigid structure that is very efficient. It has lots of open space. It's usually spanning some kind of gap, like a bridge or a river, or across a ceiling. But it's the whole point of it being like a large, efficient, open structure. Because think about it, if I wanted to build a roof for a house, okay, here a little sketch off to the side. Let's say I want to build a roof to a house. I've got two walls, a floor. There's my two walls. There's my foundation slab. Everything's there in place, and I get to doing the roof. I'm pretty happy. I've planted my flowers. Sun is shining, but it shines a little too strongly, and then also there's rain coming in sometimes, about 3 times a year in Santa Barbara. So I need a roof. Now I could get a massive slab of, say, concrete. Okay, sometimes roofs are made like this, especially when there's going to be another floor going up above, because then it becomes the floor as well as the ceiling. So I can have this huge, big slab of concrete, or, if I'm like back in the olden days, it could be massive, thick logs, or big slabs of stone or something. But those are very heavy. If for any reason the wall breaks, they are actually quite dangerous because they fall on you and flatten you. And this, because they're so heavy, they're hard to get up there in place, and it's just not necessary either. We can have these large, open, efficient structures that achieve the exact same thing. They still span a gap of some sort. They provide a structure for like a roof, a ceiling, all the rest of it. They're load bearing. When you look at bridges, they literally, can take like cars and buses and trucks and things. When it comes to the train bridges, this is actually a model, by the way. This is not life size, this is a scale model. We have very heavy loads, okay? So they're very strong, and they weren't done with just solid slabs of material. They were done with much, much less material. So they are, when I say efficient, I mean that they are cheap. They are relatively inexpensive, okay? Relatively little material for the work that they are doing. Okay, a big slab of stone or concrete is not efficient. That is the brute force method. It works, but you can do better. You can keep costs lower. You can keep weight lower. Especially if you think of like spacecraft or aircraft, you got to keep your weight down. So we use a lot of truss structures, open, efficient spaces. So the other really important thing about trusses, not only, as you can see, they can be made of wood or metal or carbon fiber or anything, but the really interesting thing about them is that all of the members, and when I say members, these are the members, okay? These bits and pieces that make up the thing, okay? Those are referred to as the members, and where they connect, those are referred to as the joints, okay? So the interesting thing about a truss is that all members only ever carry tension or compression. Now, we have not talked a lot about load this year. It just hasn't been a focus. In the full statics course that I do in a normal year, I go all into load and all sorts of things. But the idea is that these different members, they are not carrying any kind of bending, okay? None of them are being bent, twisted in any way. Each one is only being either pulled or squeezed along its axis, okay? Along its axis, like its longitudinal axis. I know I'm going kind of fast here. So think of like this big center member right here. It's a great big log of wood in this case. This thing has an axis, okay? It's the length of it that we're talking about. It's longitudinal axis. So this particular beam of wood, because it's in a truss structure, we know that it is not being bent, okay? Okay guys, I'm sorry for the little flicker there. I'm going to try something else. My video software is playing up on me, and so I'm just having to do some different things. But my point that I was making there is, as you have any kind of truss, okay, with its joints and members, I'll try to use the red and the blue consistently throughout this lecture, they are only ever experiencing tension or compression, but not ever bending. Bending is like when you take a pencil and you bend it as though you want to snap it, or you do snap it. Picture that action. That is a bending, and that is not what a truss experiences. Truss members don't experience like a grabbing at both ends and a twisting so that it breaks. They only experience either a tension, okay, as though it were a piece of string, if you can picture that, or a compression, like it's a Coke can and someone is stepping on it. That's a direct axial compression. So every member inside of a truss only experiences either tension or compression, and that is part of the trick, is to analyze just what they are receiving. They do cause slightly different effects. We're not going to get into it too much. Now these ones here are a fascinating group. We have on the left a bunch of bridge trusses, and on the right we have a bunch of roof trusses. The bridge ones are all, I believe, I had to guess, they're named after civil engineers who first designed these and employed them, like a Mr. Pratt, a Mr. Howe, a Mr. Fink. Probably not Mr. Camelback, but you can see they're all like kind of similar, sort of related. They all have the joints and member structure everywhere, and they're all made up of triangles, just in slightly different arrangements. The nope, I was going to say something, but not true. You skip that. The roof ones, obviously not intended to span as great of distances as the bridge ones, And in the roofing ones, the idea of the open space becomes even more important, because you might have an attic, you might want storage, okay, or like headspace or something. Also with the roofing ones, they can be asymmetrical. The vaults, the flat vault, studio vaults, the dual pitch, the mono, the clerestory, those are all asymmetric because houses are frequently asymmetric, and that's totally fine, whereas bridges pretty much always going to be symmetrical unless it's an intentional design choice for the sake of shock value. They otherwise, yeah, just like to be the same going both ways. Now, what's really important when it comes to the joints in particular, this is a close-up photo of a bridge that was near where I lived and worked in Haiti. It was a camelback style bridge. Okay, camelback is right there. And this particular joints in the photo was kind of like the very last one over there, just before it started to go down to the ground. And you can see, if you look at it carefully, it's got this big thing called a gusset plate. I think it's called a gusset plate. And the gusset plate has a lot of rivets, like permanent rivets, drilled, riveted. And so like if you were modeling this in Onshape, you would correctly model that as a fixed or fastened situation between the different members. Remember, these are the members, and this is the joint. However, even though in real life they are usually bolted together in a very fixed / fastened way, it is better, easier, more conservative to model them as pin or hinge joints. Okay, like when you're looking at the textbook on page 244, let's say, where he shows the how truss, the bowstring truss, the scissor truss, all those black dots, those are all pins or hinges. Okay, they don't resist moments. They are completely like floppy, if you like, and it's the fact that they're a bunch of triangles connected together, that's what gives them their rigidity, not the strength of the joints. Okay, it is not the strength of joints. I'm saying that again, it's so important. The joints aren't holding this thing together. The joints are just pinning all the different members together, but it's the rigidity of the triangular structure which gives the whole thing its strength. And that also means, I guess, by extension, that if you take away even one of those members, the whole thing is probably going to collapse. Maybe you do have some redundancy somewhere in the truss, but if it's a minimal truss, then you don't, and everything is critical. Okay. I think what I want to do now is get into the analysis. That's kind of all our soft introduction there. I would have given more, but as I say, my video software is not working very well today, it seems. Now, I'm hoping that you've read all of the book reading. I know it will have been a lot to swallow, so I thought my time would just be best spent actually just walking through that and kind of re-teaching it, so you're getting it both in your own read way, then also in my with my instruction. So let's try to do that right now. We're looking at page 245. And we're just going to do what they do. We're going to use all the same numbers, all the same shapes. His, let's see, what is he using? Okay. Now this is probably some kind of a bridge truss because everything is very symmetrical. And by the way, the symmetry is very important. And I actually want to go see which truss is this? Let's see. This is a Pratt truss, definitely a Pratt. Yep, the Pratt has the members pointing like down in toward the center bottom. The how points up towards the center top. Okay, so the symmetry is critical. The symmetry works in our favor because as long as the loading is also symmetrical, and it is in this case, that means that you can assume that whatever's happening on the left is happening on the right. You only have to analyze half the truss, in other words. Okay, half the truss. You halve your work because of the symmetry. As soon as there's anything asymmetrical about it, you have to analyze the whole entire truss. All right, first thing he does, which is extremely wise, is he labels all the joints. So you should do the same thing. He works his way around the structure in some kind of logical fashion. It doesn't matter what, as long as you pick it and stick to it. I will do exactly what he did. We have our dimensions. We have a 16-foot height, and then we have 12-foot horizontal spans. And then if you do the Pythagorean theorem, you will see that the diagonals all across this thing are 20 feet. 12 squared plus 16 squared equals 20 squared. Okay, it wasn't directly given, but it's not too hard to work out. Okay, now the loads. I'll do the loads in purple. We have a 50. Now what does K mean? Well, what do you think it means? I would infer that he means 50,000 pounds, because we're working in the US customary system. We know that from the feet, and so 50 kilopounds is the logical thing. That is sometimes called a kip, K-I-P, kip, like a kipper. If you've had kippers for breakfast, they're not too bad. This is the actual load, the 50 kips at location B and D, and then we also have a pin joint. Oh, yeah, let's say okay. Look very carefully at the diagram. We have a pin joint at this end, and then he has like a little roller at this end. The roller is just another way to show. Here, hold on. Just move my labels a little bit. Okay, the roller is just another way to show a simple support. Okay, if you imagine something literally resting on a ball, okay, it's the same as a little triangular simple support that I showed. Something that is not capable of giving any sideways resistance at all, only a straight up vertical one. He has already done you the favor of working out the support reactions, and you must have those before you get started. Because of the symmetry, you can really just know these logically. They must also both be 50 kilopounds, 50 kips. There's just no other way it can be. If you want to sit down and work out the equilibrium equation, you'd have to do a moment sum around location, let's say A. You could solve it, but for something so simple and so symmetric, let it just be. Let it work in your favor. You got a total of 100 kilopounds. Therefore, there's 100 kilopounds in total pressing back up, and it's got to be 50 on both sides. Okay, now he starts talking about drawing isolation boxes. And so before I get into it, let me tell you what the whole strategy is here. The whole strategy is that, hey, we're doing a statics course, so we know the sum of all forces is 0. We also know, by the way, the sum of all moments is 0. We're not actually going to use that today, but that is also true. So this idea is true of the whole bridge, the whole truss. This whole truss is balanced, okay? As one overall entity, there's 100K down, 100K up, 0K to the sides. It's all in balance. But think of this. If it is true of the whole that all forces are balanced, then it must also be true in part. You should be able to take any component of the bridge, and if the whole thing is static, then every single individual component must also be static just logically that has to be true. That is called arguing from the greater to the lesser. If the greater thing is true, then the lesser thing is contained within that truth. It must also be true. In this case, the logic holds. It is correct logic. That means joint C, the sum of all forces is 0. Joint F, the sum of all forces must be 0. Joint D, the sum of all forces must be 0. This is a powerful idea. It means we can zoom in with what he calls isolation boxes on each individual joints to solve the forces inside each member. That is what we're trying to do here, okay? The whole point of the analysis here is to solve the forces in each member. And which ones are those? Well, we would like to, let me just have a look, make sure I'm trying to follow what he does. We would like to solve, for example, member AB, member BC, I think member AH, member BH, member HG, member HC, and member CG. We don't need to solve GF, CF, CD, DF, EF, or DE because those are all symmetric partners of those 7 that I just listed already. CG down the middle is the only one that does not have a symmetric partner. So there are actually 7 members to find the forces of. He, in his analysis, has only done 3, it looks like, maybe. Well, yeah. Okay, we'll see how far we get. So what you do is you pick a particular joint, and he starts off by picking joint A, so we will follow suit and do the same thing. And he does a little, like he calls it an isolation box. I would personally just refer to that as the free body diagram. He does that, figure 19.3 on page 246. He does call them the free body diagrams of those joints. He has isolated joint A and he draws the free body diagram. So you say to yourself, what is joint A? Not the members, but the joint. What is the free body diagram of joint A? So, you start by drawing the joint itself, little dot with an A. Right there. And then you list the possible forces. We know that we have a 50 kilopound force straight up vertically. And then there are 2 other forces, and we know their geometry, but we don't know their magnitude. We know their direction, their angle, but not their magnitude. Because truss members can only directly pull or push. They cannot bend or do anything fancy or push things in any direction other than their actual physical angle. That means we know that there is, we'll call it with him, FAB, the force of member AB pulling directly horizontally. Now I will say, what we actually don't know right now, we don't actually know if it is pulling or pushing. Is it in tension or compression? We actually don't know. But like with a lot of things in statics, we pick one and then we work as though it were that, and if we got it wrong, it's going to come back as a negative answer. Okay, there is one more force again. We also have this one here, which is force AH. Okay, force AH. So there's our free body diagram. Now, this is a little aside. This might take me about 5 minutes to explain this next part. The 50K is straight up. The FAB is horizontal. Those are easy. The FAH, what is the angle of FAH? what is the angle? Okay, because it feels like we're going to need to do some trigonometry and find the components of FAH in order to take our force sums horizontally and vertically. But Monsieur James H. Allen III, professional engineer, PhD, has a sneaky way of getting around the sine and cosine trigonometry. He uses the power of similar triangles. Okay, look at those dimensions again on the truss. We've got 12-inch horizontal spans, 12-foot horizontal spans, 16-foot verticals, and then 20-foot diagonals. Okay, we have 12, 16, 20 triangles, in other words. Or if you want to, yeah, let me just draw that here. 12, 16, 20. You can simplify that down. You can divide everything by 4 to get 3, 4, 5. These are 3, 4, 5 triangles, okay? The most classic Pythagorean triple that exists. So what he's doing, he's taking advantage of that and saying if the force vector has to follow along in the same direction as those triangles, then proportionally it has to follow that 3, 4, 5 pattern as well. So instead of showing an angle, he actually shows the proportional triangle. And I think I will actually, just to use smaller numbers, I will use 3, 4, 5 instead of 12, 16, 20 like he did, but it's the same ratio. And that is what he's going to use on the next page, a couple of pages further on, to actually do these sums. I am going to actually go right ahead. I'm kind of skipping to page 248, and I'm going to apply the equilibrium equations for this joint right now, and then I'll come back to the other joints. So all we need right now, we don't need the truss, all we need is this little free body diagram here. Here, let's make you really comfortable with something very familiar. Let's do the horizontal force sum, which we know must be 0. And following our little sign convention that we just did right then, the horizontal forces are, FAB is fully horizontal, okay, and then we add the component of FAH. Now instead of doing like FAH, what would this be? Cosine of that angle which I drew earlier. That would have been a way to do it, but we don't have the angle, but we do have the similar triangle. We could work out the angle, but we're not going to. We'll use his method. It's a good method. It is actually, the horizontal component is simply 3/5 of the full FAH. Look how brilliant that is. It's so simple and clean. And I haven't done this at all yet this whole year. I didn't do this in the first semester. But it's a smooth way to do it. Because the geometry of the overall structure is in a 3, 4, 5 relationship, the components of those angled forces are also in a 3, 4, 5 relationship. The horizontal one is 3 compared to the 5 hypotenuse. The vertical one is 4 compared to the 5 hypotenuse. I'm just saying the same thing in different ways. I hope it's kind of sinking in as I do that. Let's see if it sinks in anymore with the vertical force sum. With the vertical force sum, we have our 50,000. And okay, yep, he's putting the K right into the equation. That's fine. And then we have plus 4/5. Remember, in the book, he, for the vertical one, would have 16/20. I think I would have rathered he kept the numbers simplified right from the start, as I did. All right, and that's it. Those are his 2 equilibrium equations on page 248, both for joint A, and then he kind of works them through. And he says, okay, Let me just work that one because it only has one unknown. I should have grabbed a calculator. 50. Okay, that's 62.5. Yeah, yes, I'm checking his work. That's exactly what I'm doing. 62.5, and it's negative. Tuck that away, and then we'll use that. We'll feed that in right here to solve that equation. 3/5 of, and you've got to keep that negative, and we'll keep the 1,000 as well. Okay, let's see. Let's put FAB over there. Anyone watch Thunderbirds? Anyone a fan of Thunderbirds? FAB? Anyone? Back to my calculator. Times 3 equals divided by 5 equals 37.5. Great, same answer. Negative 37.5k. Don't mind my children. And then both negatives will cancel out to get 37.5k. Okay, so there are our two answers. FAH is negative 62.5 thousand. FAB is 37.5 thousand. Okay, so what does the negative tell us for FAH? The negative tells us that we were actually incorrect with our assumed direction of up and to the right. See it? See it right here? Up and to the right. We were wrong. That's what the negative gives us. The magnitude's correct, but the direction is not. So I might start to fill it over here. So FAB, the member FAB is pulling away from that joint with, what was it, 37.5 thousand pounds. But member AH, it wasn't pulling up like we drew, like we guessed. It's actually pushing down with 62.5 thousand pounds. Okay, and that leaves joint A being perfectly balanced. Okay, with the 62.5 thousand pounds pushing down to the left, the 37.5 thousand pounds pulling across to the right, and the 50,000 pounds pushing up at the reaction, all of that all equals out to be 0. It balances. Okay, now picture member AB for a second. Okay, picture member AB right here. Member AB, let's just focus on that. Imagine it's a piece of steel. It's got its joints at each end, joint A, joint B. What is happening to member AB? Is it being pulled in tension, or is it being squeezed together like a Coke can in compression? Is it a rope? Is it a Coke can? If the member is pulling on the joints, see over here? See how it's pulling away from the joint? Then what that means is that that is in tension. Okay? Member FAB is in tension, and he talks through this on page 247. Okay? In tension, and you kind of have to think about that and like viscerally imagine wrestling with this thing. Okay, joint A is having something pull on it. That's what this green circle thing is here. Joint A is being pulled by member AB. If something is pulling on it, then it's got to be like a rope. Okay, we use ropes and lassos and things to pull on stuff. So that's the only option. However, member AH, the sloped one above, that one was, we learned right here, is pushing down on joint A. And the only way that it could be pushing down joint A is if joints A and H were trying to squeeze together, and it's fighting back. So there's not really another way I can say that. You just have to sort of let that sink in. But the fact is, I'm trying to pick a right good color here, that I'm going to put a T for tension and a C for compression next to those two members. Okay, member AB is being stretched, member AH is being squeezed or shortened, and that's why it's pushing back on that joint A, and that's why member AB is pulling on joint A, because it's in tension like a rope. Alright, like I say, I kind of have to leave that there. That's about all I can do. If that didn't make sense, you kind of have to watch it again or pose me some questions or just see if it keeps sinking in. Alright, let's do the next free body diagram. He does a free body diagram for joint B. Okay, here is joint B. Okay, what do we have? We have, looking at it in the textbook or right here, we have a 50,000 pound force pulling straight down. We have force AB, which we actually know what that is. I mean, I'm kind of tempted to just stick that in there right now. Force AB is 37.5. I think I will, otherwise we'll just have endless unknowns all around us. Now, look what's happening. Look how it's pointing to the left, the one I just drew. I know that's the opposite of what it was doing back when we were doing joint A. See how it's pointing to the right? That's because a piece of rope is like pulling in from each end of it. If I sort of complete the drawing here, I have to draw its partner like that. I have to draw the partner for AH, it has to look like that. Okay, it has to be equal and opposite, because remember, the members are also perfectly in static equilibrium, so their forces are also balanced. So this is one of the hardest things to understand about truss analysis, is that you kind of keep on flipping those forces. There's a pair of forces for each member acting on the joints on either end of it, and they're always equal and opposite. Just feels very Newtonian. Okay, we have a force here. This is, looking at it, this is for member BH. And then we have a force here, which is for member BC. Okay, I hope that you can see how easy this one is going to be already. We have the sum of horizontal forces, which is 0, and we have negative 37.5. And now that we've like corrected everything, we'll just use the actual correct negatives and positives, by the way. And then we have FBC going in the positive direction. I'm just going to jump in and do that right now. We can easily see, sorry, K. We can easily see that FBC is equal to 37.5 kilopounds. By the same exact token, the vertical forces look like this. That was about the easiest pair of static equilibrium equations anyone has ever had to do in the history of engineering. 50 and 37.5. We're going to go over here and we are going to fill those in. Look at that. And notice now, as I'm doing one, I'm also doing the opposite matching pair as well. So right now we have we have four. We have four members out of those 7 solved. We have AB solved. What else? We have BC solved. We have AH solved. And we have BH solved. We don't have HG, HC, or CG. Those could now be found. Let's see. He does joint C. He does joint C on page 246. I would say, if it were me, I would probably, oh man, I don't know if it's easy to do C or H. You can't jump in and do G because you don't have any known bits and pieces yet. Ooh, actually, that's interesting. I just realized something. That's fascinating. Anyway, sorry, I was musing on the fact that if you look at joint G, what do you notice about that? We don't know anything about it yet, but if you were to sit down and do the vertical force sum and the horizontal force sum, what would you quickly discover? Think about that. If you started listing the vertical and the horizontal forces, what would you find about the vertical force sum? Anyone see what I'm saying? There would only be one member, like one thing in the vertical force sum. And when you have a zero sum with only one unknown in it, that unknown has to be 0. So we actually know that member CG is a 0 force member. It doesn't have any force that's carrying. It's actually kind of redundant. It's superfluous, at least in theory. In practice, it'd probably be carrying something due to irregularities. I didn't make this part of the reading, but if you go to page 257, he actually mentioned this whole idea of 0 force members and how to spot them. So that kind of leaves us with only 2 more. And so you could solve both of those by either analyzing joint C or analyzing joint H. I think joint C would be the easier one. I guess. Maybe. Yeah. Alright, let's do it. Free body diagram for joint C. Here it is. Now this one has no external loads at all, unlike joint A or joint B, which did. This does not. It's only the internal member forces. So we have BC of 37.5. Now, due to symmetry, remember I said this whole thing has to be symmetrical. We can actually know that member CD is also 37.5. That's cool. We actually already know that member DE is 37.5. Okay, the symmetry actually lets us fill in the whole truss as we go. We know that member CG is nothing, so we don't include that. Oh man, or is it nothing? Yes, it is nothing. Gosh, you guys have caught me doubting myself. Let's see, member CH. Member CH is like this. And due to symmetry, I'm a little worried here. I'm just going to call this CH. I know that it is not CH. I know that it is actually CF, but due to symmetry, CF and CH will be the same thing. So I'm just going to write CH twice, and that'll make it a little easier for my sums. Again, I'm a little worried about what's about to happen. I wasn't really expecting this, but let's see. Did he do this one? Nope, he didn't. He just left it to us. Alright, I think I'm good. I think I'm good. Sorry guys, I know I'm sounding very, very self-doubting right now. I'm just seeing what's coming next. Maybe you're seeing it as well. Alright, let's do our little, we have a similar triangle situation again, a 3, 4, 5 triangle. Let's do the horizontal foresum. Is going to be negative 37.5k plus 37.5k minus 3/5 FCH plus 3/5 FCH. Okay, that was one of the CH horizontal components, and then the other one. One is negative to the left, one is positive to the right. Again, do you see what's happening there? Everything's cancelling. That cancelled, that cancelled. I end up with a not very helpful 0 equals 0. If I do the vertical sum, sorry, this is why I was pausing. I was trying to see if there was any way around this, but I don't see it. We have 4/5 FCH is positive and up, and the other one is also positive and up. And that means that we have 8/5 FCH equals 0. And again, that just means that the only way that can be true is if FCH equals 0. So how about that? I hope I'm not missing anything, but we just solved it and it is also 0. This doesn't feel good. I'm going to label these 0, 0, and so on. So there's only one left, there's HG, and to do that, we will need to do a free body diagram of joint H. I feel like I'm being extra messy today. It's just me. Alright. FAH. Nope, I said I was going to use the actual numbers, didn't I? We know that FAH is 62.5 thousand. And we have a 50,000 pound one going right down. We know now that CH is 0, so we're not going to include it, but we do definitely have HG. Now, am I going to do this to the left or to the right? I'm just going to go right ahead and do it to the left. I can see if the 62,500 is in the right-hand direction, then it has to be resisted by this one to the left. So I'm not even going to bother just like doing it to the right and then find out that I'm wrong and reversing it. You see what I'm saying? This one here is to the right, so I need something to the left to balance it out. I couldn't possibly have it going this direction, you see that? Otherwise everything's pulling to the right. So I'm just going to use some logic there and do this. And this is FHG or GH, whatever you prefer. And again, we have a little 3, 4, 5 triangle. What a great handy little trick. We'll do our sums. Fx equals 0, sorry, equals 3/5 of 62.5 thousand minus FHG. And that is enough for us to work that out, isn't it? 3/5 is 37.5. Well, there's that same number again, huh? We move it over to that side, which means that everything is positive. And that's our answer right there. We just found FHG. We don't even need to do the vertical sum in this case, but we do know that 4/5 of 62.5, I'm just going to confirm this, 4/5 of 62.5 really is 50, yep. So that was it, 37.5, that is over here, and that is pushing back 37.5, and I'm going to label that with a C for compression. This one was a T for tension. This one is a T for tension. Once you get the first couple of C's and T's for compression tension, just kind of look around. Don't try to wrap your head around which one it is. Just say, are the arrows pushing back out like my first C? Yes. Are my arrows pulling away from the joints like my first T? Yes. So just kind of copy that pattern around. And all these crazy zero force members. This is interesting to me. I think what's happening is this is not a real bridge. A real bridge would actually have a load in the middle joint as well, and that would then create forces in CH and CG. But because they didn't put that in the analysis, that's why this feels kind of fake. That none of that stuff in the middle is doing any work at all. So that is the end of this analysis. We got there. You guys don't know, but I did several retakes in the background because of my video software. That was fun. And we can sort of now confidently look around the whole truss and say, like, you know, what's the worst thing that's happening? Well, the worst thing that's happening on this whole truss is member AH, this guy right here. He has the highest load of 62,500 pounds. And so that's the one you should probably like pay attention to. Like that's the one that you should design, that you should use that number for your designing how thick and how sturdy the members around the whole thing are. You know, use the heaviest, most in danger one out of the lot. And that's it. But I think that's where we'll leave it. We have covered so much ground. We just did a full truss analysis and explanation in one video. In the second video this week, I will do a different one. And we're just going to get more and more used to this. And you will be a pro before you know it. Look out for that assignment as well. It is out there on Google Classroom. Make sure you drop something on the discussion board, a question or a comment. I'm expecting plenty. But yeah, you're going to feel better as you do more practice with these. All right, thanks guys. Have a good rest of your day.